Let's practice entropy balance with an open system, and in this case, our goal is to compute the rate of entropy generation from irreversibilities, which is sigma dot. So imagine that we're given a steady flow of ideal gas nitrogen, molecular nitrogen, and that the mass flow rate is 2 kilograms per second going through a cylindrical pipe that looks something like this, so the sides of the pipe are parallel to one another. We also have a heat transfer involved as gas flows through this pipe that is 50 kilowatts, and it's coming from a hot reservoir at temperature 410 Kelvin. So that's transferring energy into our system as the gas moves through the pipe. The inlet temperature is 400 Kelvin, the inlet velocity is 200 meters per second, and for the exit values, well, actually it's going to maintain its temperature so that the exit temperature is also 400 Kelvin. The exit velocity is 300 meters per second. Now you may look at this and say, wait a second, how did it speed up? Well, we are adding heat energy to the system. We also know that there are irreversibilities generated. Probably there are interesting processes happening within this pipe that we don't know about, but we don't need to model them in detail. All we need to know are the inlet and exit conditions and the heat transfer. We should be able to apply entropy balance to figure out what the entropy generation had to be. So for a steady state, ds dt has to be 0. That tells us that 0 actually equals q dot h over th plus m dot S1 minus S2 plus sigma dot CV. So what I've done is I've set ds dt equal to 0 on the left-hand side. We have one heat transfer, so that's the q dot h over th. And then remember, the m dot terms represent entropy advected in through the inlet and exited out through the exit. Sigma dot, as always, represents the entropy generation from irreversibilities, which is what we're trying to solve for. So let's rearrange to solve for sigma dot. So I do that. And you may notice I have to get my signs right, so now q dot h has a minus sign in front, and I've shifted the order of S2 and S1 to account for the correct signs. So now we need a way to evaluate S2 minus S1. Well, we know how to do this for an ideal gas, right? You can look up in your lecture notes that for an ideal gas, the change in specific entropy is this integral of CV dt over t plus r ln of the ratio of specific volumes at the exit and inlet. Or in the case, if you're thinking of this as a process, the end state divided by the initial state. Okay, so we can simplify this because that integral has to be 0, right? We're going between the same temperature. Limits of integration are identical. That means that the integral is 0. So S2 minus S1 becomes r ln of little v2 over little v1. Let's plug that result into our expression for sigma dot. So we do that. All right, now we know a lot of these quantities, and I'll move that up. Well, we need to evaluate those, the ratio of little v2 to little v1. Well, we can get that through the mass flow rate. So obviously in a steady flow, m dot I has to be m dot e. There's only one inlet and one exit. And if you remember, you can write m dot as either the density times the area times the velocity, or the area times the velocity divided by the specific volume. That latter one will be more interesting for us. So a times the velocity over the specific volume is the same at the inlet and the exit. And just to be absolutely clear, you can substitute in that the exit specific volume is little v2 and that the inlet is little v1, right? You can think of this either as inlet and exit or as a process happening to one parcel of gas. It's equivalent. So our goal is to solve for little v2 over little v1. So little v2 over little v1 equals the ratio of little v at the exit to the inlet, I just said. And we can rewrite that in terms of areas and velocities. Now, just using the expression we got using the m dots. So we can cancel out the areas. It's a cylindrical pipe. The area is the same at the inlet and exit. That tells us that little v2 over little v1 is the exit velocity divided by the inlet velocity. So let's plug that back into our expression for sigma dot, which we do. Move that up, and now the nice thing is we have all of these values, right? And remember, the value of q dot h that you insert should be positive. It has a negative sign out front, but that's fine. So we'll put in all these numbers, making sure to put in the correct R for molecular nitrogen, which we do. And that first term, which is negative, is minus 0.122 kilowatts per Kelvin. The second term will be 0.241 positive kilowatts per Kelvin. So we add those together to get 0.12 kilowatts per Kelvin, or if you prefer, 120 watts per Kelvin. So that is the rate at which entropy is being generated within our system, and it's a positive number, which is not surprising. Any real system with irreversibilities is going to lead to a positive value of sigma dot. You're absolutely prohibited from having a negative value of sigma dot.